Hello everyone, welcome to another video by the YouTube Lab of Everything. As you know, today we will be discussing about motion, which is the third part of our motion series, which is the grade 9 NCERT chapter 7. So today we will discuss about distance time graphs, velocity time graphs. So stay tuned to know about it. Let's get started. Let's get started. So first we need to know the basics of distance time graphs, which we'll be starting with. So I will use a red color pen for marking. So now I will show you how it looks when an object is at rest. So when an object is at rest, you can draw a horizontal line which is parallel to the time at any given point on the y-axis, which is the distance moved in meters, or you can keep it meters, kilometers, etc., etc. Make sure you have given distance moved in brackets the units, and on the x-axis time and the units in the brackets. This is compulsory. Your marks might get cut because if you didn't mention it, so that's very important. Back to this. So this is how you represent an object at rest. So now if I draw a horizontal line parallel to the time, which is the x-axis, it means that the object is at rest. But this means completely different according to the velocity time graph, which we will discuss soon, so stay tuned. So now let's get back. Now let's see how to represent an object moving in uniform motion. So let's say the object starts at 0 and it moves diagonally straight. Now this is how you represent an object going in uniform motion. So you can see that every 1 meter, the green color is an imaginary line. So every 1 meter it's traveling every 1 meter 1 second. So that's how you can show that the object is traveling in uniform motion, as you can see. So 1 meter 1 second, 2 meters 2 seconds, 3 meters 3 seconds. So goes on. So that's how you can show an object going in uniform motion. Now let's see how can you represent an object going in non-uniform motion. This is a curved line. It can either, the non-uniform motion can either be like this, or it can be like this. Both of these are correct for non-uniform motion, because as you can see, for 1 meter it isn't covering I'm talking about this one, okay? So for 1 meter it isn't covering 1 second, but for 2 meters it's covering 1 second, and for 3 meters also it's somewhere like 1.2, and for 4 meters it's at 2 seconds. So the motion is completely varying. So that's how you can represent non-uniform motion on a graph. So that's how you can explain that an object is moving in non-uniform motion in the graph. Next, we will talk about how do you represent an object coming back to its original position. So let's say an object starts at, so let's say you start at your home, you reach school, and you return back to home. How do you represent you coming back from school to home? It's simple. Draw a downward slope towards the time, which is the x-axis. This represents that the object has returned to its original position. Now let's take this example seriously and plot it in the graph. So this is going to be easy. Let me just show you. So you start at your home, which is 0 distance and 0 time. You start and then you go to school. Let's say it's at 4 meters. So you reach home, you reach school, and you stay for some time, and now you come back home. So over here the time is actually in hours. Okay, so you come back, now you want to come back home. So how do you represent that? By just drawing a downward slope. Now you can see that this is in a shape of trapezium. Now I'll tell you, this is you going to school, this is you in school, this is you returning home. So that's how you can represent an object going to a place and returning to its original position. Now let me show you a different example, and you're gonna tell me how the object is traveling. You might have seen this graph somewhere. So it's simple. An object is moving to a position A. Let's say this is its original point. An object is moving to position A, stays there for some time, and then again goes to a position B, stays there for some time, and then again returns back to position O. So that's how you can represent an object going to two places, staying in the two places, and returning to its original position. So that's how the graphs work. Let me tell you something very important which I have missed. The more steeper the slope, the more faster the object is going. Let's say this is a slope for object A, and then there is another object B, starting from the same position and reaching the same position a little faster. This is object B. Now you know that object B has traveled faster than object A because clearly it has taken more time to come to the same point, whereas object B has only taken a less amount of time. Look at this. Now there's another way where you can see, I mean, this is like common sense. If there's another way, let's say in the exam they ask you to clearly show how it has happened, how the object A is faster than object B. So let's say object B does 5 meters in 9 seconds, and object B does the same 5 meters in 6 seconds. Now you're gonna draw a line, let's say at 3 meters, anywhere. You can draw it anywhere below 5 and above 0. So now you plot the lines, the points. So here is the intersection of B and here's the intersection of A. So now you draw a downward slope here and you draw another downward here. So you can clearly see that this timing is more than this one. Even if you draw the same line on the 5 meters exactly, you get the same thing. You get the same distance, which is over here. Let's say the distance between these two is 1 centimeter. If you draw the same exact line over here, it's the same exact 1 centimeter. So that's how you can see. Now you can see that object A has traveled faster and reached the same point than B. I mean, the other way around. Object B has traveled object A faster. Okay, that didn't come right. So that's about distance time graphs. Now let's move on to velocity time graphs. Now let's talk about velocity time graphs. So to show that the object is at rest in a velocity time graphs, we need to draw a horizontal line on the x-axis over here. So when you draw a line like this on the x-axis, it means that the object is at rest position. Because if you draw it somewhere over here, it would mean that the object is moving at 4 4 meters per second. So that would be totally a wrong meaning, right? So that's what I've told you in the beginning. It's completely different if you draw the same line in a velocity time graph. Now let's see what happens when you draw a line over here. Let's say 5 meters per second. This means that the object is moving in uniform motion. So that I'll show you imaginary line. So 5 meters per second. So once the first second is going 5 meters per second, the second it's also going 5 meters per second. So like that it goes on. So we can see that the object is moving at 5 meters per second every second. So that means, so now you know. Now let's see how you can show acceleration in a velocity time graph. So when an object starts at 0 velocity and it increases its speed from 0 velocity to 5 velocity in 5 seconds, this is uniform acceleration. Now I can show you non-uniform acceleration. It's the same as non-uniform motion in a distance time graph. It goes in a curve or in upward curve. So this is non-uniform acceleration. Now let's see an object increasing its acceleration other than 0. Like let's say an object is traveling at an acceleration of 3 meters per second and it increases to 3 meters per second to 4 meters per second and then to 5 meters per second, and then it goes uniform motion and again it increases, uniform velocity, and then it again increases to 7 meters per second. This is how you can show that the object is going in a non-uniform velocity. It starts at 3 meters per second, reaches 5 meters per second, and again it goes in 5 meters per second for around 8 seconds, and then again it goes in 7 meters per second. It increases its acceleration. So what would be the opposite of acceleration? Deceleration, right? So I'm going to show you an object going decreasing its velocity. Yes. Now the object is going from 7 meters per second in uniform motion, and from the third second it goes 6 meters, then 5, 4, 3, 2, 1 meters per second, and then it comes to a stop. Now the object has stopped when it reaches over here or anywhere on this time graph. The object has stopped. That's what we said in the starting, right? When the line is on the time graph, the object has stopped. So this is how you can show deceleration in a velocity time graph. But in a distance time graph, the same line means that the object is returning to its original position. So that's about distance time graphs and velocity time graphs. Now let's move on to equations of motion. I've discussed these equations in my other video, kinematics. I will link it in the top right corner, put it in the description below, and put it in the end screen. So please do check it out. I've said the same thing in my previous 2 videos. If you didn't check them out too. I'll leave the link in the description below and put it in the end screen. It's on the top right corner as well, so check it out. Okay, now let's discuss about equations on motion. So equations of motion, there are 3 equations of motion given in your textbook. When an object moves along a straight line with uniform motion, it is possible to relate its velocity, acceleration during motion, and the distance covered by a certain time interval by a set of equations known as equations of motion. So that's the line given in your textbook. So it basically means that there is a relation between the initial velocity, final velocity, acceleration, time, and displacement. So all that relations are given in 3 formulas. The first one is final velocity equals initial velocity plus acceleration into time. The second one is displacement equals initial velocity into time plus half into acceleration into time square. Another one is 2 into acceleration into displacement equals velocity square final velocity square minus initial velocity square. I have completely given the detail in the screen. Make sure you take a screenshot. So the first velocity to the initial velocity time. The second equation gives the displacement of an object as a function of time, initial velocity and acceleration. The third equation relates the final velocity to the initial velocity, acceleration and displacement without involving time. So the third equation is a little I've put it from your textbook, but it still means the same. 2 into axle 2as equals v square minus u square is the same thing as v square equals u square plus 2as. Basically the same thing. Any use, it's the same thing, you get the same answers. So that's about equations of motion. Now let's go on to uniform circular motion. It's a very small topic, we'll finish it real quick. So let's go. Uniform circular motion. So in your textbook there are 4 different diagrams, but I will explain with only this one. So they start with talking about velocity. So now let's say the speed of an athlete running around this track is constant, 5 meters per second. Then but the velocity keeps changing even if he's moving 5 meters per second, because the direction is keep changing. Speed is just magnitude, but velocity is magnitude plus direction. Hence velocity might be non-uniform, but the speed might be uniform even though the magnitudes of both are the same. So that's what they're trying to convey through the uniform circular motion. And they have also given you a formula to calculate the speed of the person. Not speed, velocity, or it's the same as speed if you take the displacement. So it would be 2 pi r divided by time. This is the formula they have given you, and based on this they have given you a question, exercise the question 1. That's also based on the same concept, 2 pi r divided by t. So it's very simple. An athlete starts over here, he completes 3.5 rounds and he reaches here, and the displacement would be the radius, which is 200, and the distance would be 3 rounds and a half. So that would be 2200 and meters. That's the distance, and 200 meters is the displacement. So that if you want me to solve that question in detail, I can do that. Just comment down below. So that's basically about uniform circular motion. Also there's an activity over here to tie a thread to a small piece of stone and spin it around. Notice that when you spin it around and leave it, it would go straight in the direction which you have left. So that's one thing you need to observe, and that's it. Other than that, there's nothing else regarding uniform circular motion. So I guess we could end this video. Also, make sure you look at the end screen because the videos I have mentioned will be on it. Thank you for watching my video. Come back for more videos like this, and we end our motion series, by the way. So the videos I've mentioned: kinematics, motion part 1, which is the overview of motion, and motion part 2, which is the actual chapter, would be on your screen right now. So make sure you check them out and let me know in the comments what do you want to discuss next. And take care. See you. Bye.